In some specific cases, static equilibrium of 3D frames becomes a little complicated and tricky. In this presentation, we're going to go through a full detailed example on 3D frames in equilibrium that requires some previous knowledge in statics and vector operations. I hope that this tutorial will clear up questions you might have about this topic. Before we get into the details of this example, make sure you watch all the way to the end of this video. This is our example, and here we have a 3D frame. This frame is supported by a ball and socket at point A, a ball and socket at point D, a cable at point E which is fastened to the wall at point G. This frame is supporting a weight of 450 pounds downward. It's required to find the tensile or the minimum tensile force in cable EG and the location of point G that will give minimum tensile force in the cable. Solution. We will draw the free body diagram of the frame and then we will set the point of origin at the wall. This is the lowest point in the structure. At point A, we have 3 rectangular force reactions. At point D, we have another 3 rectangular force reactions. The reaction at point E is a tensile force which acts away from the member in the direction of the cable. The cable provides a balancing force that resists the overturning tendency caused by the weight W. The coordinate of point E is 6 in I, 12 in J, and 6 in K. The coordinate of point C is 12 in I, 12 in J, and 6 in K. Notice that if we sum the moments about the axis AD, the reactions at A and D will be eliminated from the computations. In order to do so, we need to define a unit vector in the direction of AD. A unit vector AD is nothing but a position vector in the direction AD divided by the magnitude of this vector. The position vector AD is 12 in I plus 12 in J minus 6 in K. The magnitude of this position vector is the square root of 12 squared plus 12 squared plus negative 6 squared. The result will be 2/3 in I plus 2/3 in J minus 1/3 in K. Remember, this is a unit vector that defines the direction of the axis AD. The moment about the axis AD can be calculated with respect to any point on this axis, to any point that lies on the line of action of the force. In this example, the moment about the axis AD will be calculated with respect to point A. If the frame is in equilibrium, then the sum of the moments about the axis AD should be 0. Now, let's sum the moments about point A. We have the moment arm AE times the tensile force T. In vector form, the cross product of the position vector RAE and the tensile force vector T, plus the moment arm AC times the weight W. In vector form, the cross product of the position vector RAC and the weight vector W. As we know, the cross product of the position vector RAE and the tensile force vector T is another vector perpendicular to both of them. The projection of this new vector on a unit vector UAD will give the moment about the axis AD. Similarly, the cross product of the position vector RAC and the weight vector W is another vector perpendicular to both of them. The projection of the new vector on the unit vector UAD will give the moment about the axis AD. Now we are ready to calculate the position vector RAE. The position vector RAE moves 6 feet in I and 12 feet in J. The position vector RAC moves 12 feet in I and 12 feet in J. The weight vector W is negative 450 in J. Why is it negative? Because the weight W is pointing downward in the negative Y direction. The tensile force vector T is nothing but the magnitude of the tensile force multiplied by a unit vector in the direction of the cable EG. The tensile vector is completely unknown, and we are solving for this vector. Now let's go back to equation 1. Notice that this equation consists of two terms. This type of a vector operation is called the scalar triple product. The second scalar triple product can be calculated since all vectors have been defined. If we do so, we will get 1800 pounds-foot. Remember, the scalar triple product produces a scalar quantity. Now, if we substitute this value into equation 1, we will get the first scalar triple product equal to negative 1800 pound-foot. I will briefly show you how to perform the cross product of two vectors and the scalar triple product when we get to the end of this tutorial in Appendix A. My question now is, can we solve for the unknown vector T or the tensile force vector T using the scalar triple product equation shown here? The answer to this question is no, we cannot do that unless we rearrange the terms and use the rule of minimum dot product of two vectors. Now we can use the commutative property of a scalar triple product. This scalar triple product can be rewritten as shown here. And the new scalar triple product should equal to negative 1800. The cross product of the unit vector AD and the position vector AE can be calculated because both of them have been calculated. The result will be a new vector, and the new vector will be denoted by vector V. Now we can calculate a unit vector in the direction of vector V. By now, I think we all know how to do that. Now let's investigate the following scalar triple product. The cross product of the unit vector AD and the position vector AE is a new vector V perpendicular to both of them and pointing in this direction. How do we know that the new vector V is pointing in this direction? Use the right-hand rule. Curl your fingers from the unit vector AD to the position vector AE. Your thumb points along the new vector V. The projection of vector T onto the new vector V is the dot product of vector T and V. Notice that the new vector V is in opposite direction to vector T. The students should know that the dot product of two vectors is minimum when the cosine of the angle between the two vectors is minimum, or theta equals 180 degrees. In other words, if the two vectors are parallel but they have opposite directions, then the dot product is minimum. What do I mean by this statement? This statement means that if vector V and the tensile force vector T are in opposite direction, which they are, and they are parallel to each other, then the projection of vector T onto vector V will be minimum. What does it mean? It means we will get the minimum tensile force in the cable. And what do I mean by the projection of vector T onto vector V? It means the dot product of these two vectors. If the tensile force vector T is parallel but in opposite direction to the direction of vector V, then the unit vector in the direction of the tensile force should equal to -1 times the unit vector in the direction of vector V. This is shown in equation 5. Now, if we substitute equation 5, equation 4, and equation 3 into equation 2b, we will get equation 6. If we perform the dot product of these two vectors and simplify the result, we will get the minimum tensile force in the cable. In this case, the minimum tensile force in the cable is positive 300. In vector form, T minimum equals negative 200 in I plus 100 in J minus 200 in K. Can you prove it? Now we can double check that the minimum tensile force T minimum is 300 pounds. How to do that? Take the square root of minus 200 squared plus 100 squared plus negative 200 squared. Location of G. Since the vector EG and the force T minimum have the same direction, their components must be proportional. At point E, we have 200 pounds in the negative x direction, 100 pounds in the positive y direction, and 200 pounds in the negative z direction. We also have x prime in the negative x direction, y prime in the positive y direction, and z prime in the negative z direction. Notice that z prime is equal to 6 feet. The proportionality between forces and distances can be expressed as negative 200 over negative 6 equals 100 over y prime equals negative 200 over negative x prime. Therefore, the coordinate of point E prime will be negative 6, 3, negative 6. The coordinate of point G measured from the point of origin of the system is the algebraic sum of the coordinates of the 2 points E prime and E. The coordinate of point G can be shown to be 0, 15, and 0. In Appendix A, I will be showing you how to perform the cross product of two vectors and the scalar triple product. Let's start off with the cross product of two vectors. Here we have two vectors, RAC and W. And it's required to find the cross product of these two vectors. First, start with I, J, K. Write I, J, K. This is our first row. The second row is the components of vector RAC. We have 12 in I, 12 in J, and 0 in K. The third row is the components of vector W. We have 0 in I, negative 450 in J, and 0 in K. Now we need to find the value of the matrix determinant. We need to find the value of this matrix determinant. How to do that? Hide all elements in row 1 and in column 1 except element 1. Then multiply I by 12 times 0 minus 0 times negative 450. The next step, hide all elements in row 1 and in column 2 except element 1, 2, then multiply J by 12 times 0 minus 0 times 0. Hide all elements in row 1 and in column 3 except element 1, 3. Then multiply K by 12 times negative 450 minus 12 times 0. Remember, the sign sequence is plus, minus, plus. The sign sequence is plus, minus, plus. Now let's move on to scalar triple product. Write I, J, K. This is our first row. The second row is the components of vector UAD. We have 2/3 in I, 2/3 in J, and minus 1/3 in K. The third row is the components of vector RAC. We have 12 in I, 12 in J, and 0 in K. The fourth row is the components of vector W. We have 0 in I, negative 450 in J, and 0 in K. Since scalar triple product produces scalar quantities, the first row I, J, K can be eliminated, and the result will be a reduced matrix determinant. Next, hide all elements in row 1 and in column 1 except element 1, 1. Then multiply 2/3 by 12 times 0 minus 0 times negative 450. Next, hide all elements in row 1 and in column 2. Hide all elements in row 1 and in column 2 except element 1, 2. Then multiply 2/3 by 12 times 0 minus 0 times 0. Next, hide all elements in row 1 and in column 3 except element 1, 3. Then multiply negative 1/3 by 12 times negative 450 minus 12 times 0. The result will be 1800 pounds. Remember, the sign sequence is plus, minus, plus. Again, the sign sequence is plus, minus, plus. Now we need to find the cross product of vector UAC and vector RAE. Write I, J, K. This is our first row. The second row is the components of vector UAC. We have 2/3 in I, 2/3 in J, and negative 1/3 in K. The third row is the components of vector RAE. We have 6 in I, 12 in J, and 0 in K. Hide all elements in row 1 and in column 1, except element 1. Then multiply I by 2/3 times 0 minus negative 1/3 times 12. Next, hide all elements in row 1 and in column 2 except element 1, 2. Then multiply J by 2/3 times 0 minus negative 1/3 times 6. Next, hide all elements in row 1 and in column 3 except element 1, 3. Then multiply K by 2/3 times 12 minus 2/3 times 6. The result will be 4i minus 2j plus 4k.